Oh, I love watching TV. But you know, TVs like the one that I'm holding here are able to display millions of different colors. Even these small older ones do a tremendous job. But what is it about the TVs that makes it so that we can see all the colors? There must be something in here. And is it millions of colors that are embedded in it? Or is it something else? Is it something simpler? Does it have to do with our eyes? Well, that's what we're going to investigate today on Galileo's Universe. You know, watching TV can not only be educational, but we can also learn quite a bit about the TV just by looking at it. Well, for example, one of the questions I have is, how can we see all the colors that are produced by this tiny screen? And whether it's a small screen like this, or a big screen that may be hanging up on the wall, or even something that's projected, these TVs produce millions of colors. Well, how is it that we can see the millions of colors? And what is it about ourselves that allow us to see not just the colors from the TV, but also outside in everyday life? Well, that's the big question that we have today. How can we see all the colors of everyday life? And that's what we're going to explore next on Galileo's Universe. So in order to understand how we see the colors that come from the little TV or the big TVs or whatever TV, we have to understand a little bit more about the basics of color. Now I have a question for you, and I want you to think about this. What are the primary colors? I will give you a second. You've had a second. Now if you said, for example, red, blue, and yellow, well, many people think that. And you might have also said red, blue, and green, or maybe cyan, magenta, and yellow, or maybe black, blue, and green. Well, it turns out that one of those sets is correct. Well, no, two of those sets is correct because I sort of did this as a trick question. There are actually two sets of primary colors. And we're going to start off first by looking at the primary colors of light. Now, for those of you who said red, blue, and yellow because you learned it in the art class, you may be surprised by the results that you're going to see in this demonstration. So let me show you what I've got here. I've got 3 light bulbs. These are floodlights. So I've got a blue light bulb, I have a red light bulb, and I have a green light bulb. And I've got other things set up because it turns out that these light bulbs are a little not pure. They give off other colors other than just the pure blue, the pure red, and the pure green. So I'm going to use these filters. And the filters will really make sure that I'm only getting out blue, red, and green light. And then we're going to take a look and we're going to do what's called color mixing. Now in baking, when you bake in your kitchen, you take ingredients and you mix them and you add them together. Key word there is adding things together. Well, those are more than a key word because those are several words. All right, and we've got a green filter. So I'm going to put this on here. And then we're going to turn these on in sets. But, you know, a lot of light here, so we're going to go ahead and take care of the lights. 3, 2, 1. Love the timing on those clappers, don't you? All right, so let's take a look. So I'm going to turn on all 3 lights, and I'm going to turn, let's say, 1 out. So right now, I have the blue and the green. Now, of course, it's projecting up, so we're going to need to see the light shining off of something else. So we're going to use some reflection, and it turns out I'm going to hold this up. And the mixing of the blue light and the green light in here forms a color called cyan. Now I'm holding my hand up here so that you can see in the darkness, the shadow of my hand, that there is blue and green that's mixing there, and in between is this color called cyan. So I've added two colors together, blue, green. All right, so blue and green have made another color, so they've added together. All right, let's take a look at a second combination. Let's do the blue light with our red light here. So again, remember, we've just got filters over the top so that we've got very pure blue and very pure red. All right, I'm going to hold up the whiteboard again, and you see, wow, look at this. You see a different color. Now, it sort of looks reddish, but this is a color called magenta. And magenta occurs from mixing blue light with red light, and again I'm holding my hand up there, so in the shadow of my hand you see blue and red. All right, all right, so I've taken those two. Now, for those of you who said that the primary colors are red, blue, and yellow, now the whole idea behind primary colors is that you cannot make red, blue, or yellow out of any other combination. Let's see if that holds true. Let's now try red and green light. We'll turn these on and hold this up, and what do we get? Turns out that we get yellow light. Now wait a minute. If yellow, as you may have learned in your art class, is a primary color, we shouldn't be able to make it here. Look at this. We have definitely made yellow light out of red and green. So it turns out that these three primary colors of light, red, blue, and green, make all the other colors that we see. So it's these three basic ones. Now I'm going to turn all three on, by the way, just so that we can see the effect of all of them. And when I have all three together, a little hard to tell, but I'm going to hold my hand up, we have white light. And if I had these far enough away, we get a lot of white light. Now, if you've ever been on a stage in the theater, you notice that they will use red, blue, and green lights up above to produce white light down on the stage. All right, so these are the three primary colors of light. But what about pigments? So let's go back and turn on our lights again. Ready? 3, 2, 1. I love those clappers again. They're good timing. All right, so turn these off, and we're going to take a look, because these are additive. We start with no light, and we add them together, and we produce other colors. So I've got here 3 color discs, and if I put, let's say, yellow, which all of you might have said was a primary color of some sort, and you mix it with what looks like blue, but this is not blue, this is cyan. Remember, we've already heard about that word. When we mix the blue and green light, we get cyan light. So I've got a cyan disc, and when I mix these together, you notice I get green. So there's 2 sets of primary colors. There's this primary color of light, and then there's primary colors of pigments. So these are the color pictures you see in the newspaper. These are the color pictures you see in advertisements, in books, anything where it's in print form. All right, so I mix those 2, and I have yellow, cyan makes green. All right, what about if I take a magenta disc, and a yellow disc, mix them together, and I get red. Now, if you have a color printer at home, one thing that might happen is if you run out of your yellow, you end up getting this really pink writing on your printout. And that's because you've run out of yellow. And yellow is required to make red when you're printing something, like on a color printer. And then finally, when I mix cyan and magenta together, I get what should be blue. These are not really the best discs, but they are pretty close. So this is blue. And then finally, mixing all 3 together, in between, we get black. So what we're doing here is we're starting off with light. In order for us to see color reflected off these discs, we have to be able to start with white light. White light shines on it. Things get subtracted away, And when I mix all three pigments together, I have black light in the center. However, in order to see these colors in the first place, there has to be something else going on, and it has to do with our own eyes. Well, we're going to take a look at how our eyes work coming up. Welcome back. All right, well, now that we know that there are two sets of primary colors, there's the primary colors of light, which are, thank you, red, blue, and green, and then there's the primary colors of pigments, which are, thank you, cyan, magenta, and yellow. We really need to understand why we can see these colors, and really, why is it red, blue, and green when it comes to light? All right, well, we really have to sort of get inside of our heads. Now, I don't really feel like ripping open my eyeball in my brain to take a look at why we see these primary colors. So the next best thing that we have is a model. So let's take a look at our model here. This is the model of an eyeball that we've sort of cut open, and it's much larger than my eye, as you can imagine. And so inside, we have at the back of our eye a place where there's a couple structures. And these two structures are responsible, one for allowing us to see color, and the other one for letting us see just sort of light. You know, because at night, it's very difficult to see color. So what we've got here is the light will go through the front of the eye, will go through the lens, and get focused on the back here. So these structures that allow us to see color are called cones. Now, they're very small, and they're not even shown on here. So we're going to zoom into this, and when we zoom in, we can see another model over here, and they are our cones. So inside of our eye, we have a blue cone, we have a red cone, and we have a green cone. And of course, they're made out of cones. And then around this, I've got these other things that I'll talk about in a second, and they're the rods. All right? But it's these three cones that are not just, there's not just one of each in our eye, there's millions of them that are responsible for detecting light. All right? Now, what is light? Because that's the other thing we've got to figure out. Well, light actually has sort of a dual nature. Scientists say it's the dual nature of light. And the reason is because sometimes it acts like a wave, like a water wave, travels like a water wave, and sometimes it acts like a particle, like a ball. Well, in this case, we're going to represent light, and I've got a blue, a red, and a green, and a yellow, and I'll show you why we've got the yellow in a second, that represents light. Now, these are emitted from all different kinds of atoms, and it occurs when we have energy, could be electricity, that goes into an atom and causes this atom to gain energy. Now, you imagine if you eat a candy bar, you gain energy. And you gain enough energy so that you're able to stand up on a chair. But you're not allowed to stay there because your parents tell you you're not allowed to stand on the furniture. So you jump back down. Now, when you jump back down, you release energy. It turns out that in atoms, they gain energy from electricity. They can't stay in this energetic state, so they release different colors of photons. And these photons go flying, and they're all over the place. And some of them come into our eyes. And when they do that, they start to excite these cones. So if I have a green photon of light, this green photon comes in, strikes only the green one. It only activates the green one. Now, it could strike over here, but it does nothing. It only turns on the green one. Then that green cone fires off information to our brain so that we see green light. Same thing with the blue photon. The blue photon comes down. It may strike any of these, but it only activates the blue photon or the blue cone. That sends information to our brain and we see blue light. And then finally, if I have a red photon, it comes in, hits the red cone, sends information off to our brain. Now what happens, because we see in many different colors, what if we have a yellow photon? Well, as we remember in the last segment, yellow light is the combination of green and red. So this yellow one will come in here and actually will strike and activate both of these. So it causes both of them to gain energy and turns on both of them, and our brain interprets the combination of the red and the green as yellow light. Now, turns out that dogs see really only blue and yellow. At least that's the current thinking among scientists. They may see sort of toward the violet or maybe a little toward the red, but they think that it's mostly centered around the blue and yellow range. So they see only two colors, and they've only got two sets of cones. We have got these three sets of cones, and it is because we've got red, blue, and green cones that the primary colors of light are red, blue, and green. Now, I mentioned a second ago that we've got these things out here. Turns out that if you go into a darkened room, you need enough light to turn on the red, blue, and green. And in that case, when you go into a dark room, you can't see any color. Go try it. I'll wait. Come back. Because when you do that, you only see really shades of gray. And when you see shades of gray in darkened room, it's these rods that are turning on. And light still comes in from the various colors here, but they're only able to activate these. There's not enough to turn these on. All right? So it's because our eyes have got red, blue, and green cones that we're able to see red, blue, and green light, and that's why they're the primary colors, red, blue, and green. All right. So really the next question is, then how does this all work in getting into our television sets? That's what we're going to take a look at next. All right, so before we go ahead and take a look at the TV and how it works, let's take a little bit more on how we can see these different colors. And I'm going to use these wonderful glasses. Now, these are just not the wonderful fashion statements that you can wear around the neighborhood. They actually are special types of glasses that have a plastic in it that's called a diffraction grating. And the diffraction grating has scratches in the plastic so that when light goes through, it breaks it up into its colors. So, you know, this is sort of like cooking again, because baking, we have all the ingredients that go into a cake. But we sometimes want to know, well, what's in the cake? It's a little difficult to separate all of the ingredients out, but these are able to do that with the light. Now remember, our eyes can only see red, blue, and green. So like if we have a yellow photon or yellow light, we activate a couple of these colors. But we can look at that yellow light and separate it out. So let's take a look at three different colors. I have a red light, I have a blue light, and then a green light. All right, well, let's take a look at these colors. And, oh, wait a minute, you need one of these as well, right? So let's put this on you so that you can see what I'm seeing. Take a look at these colors. Now, if I look at the blue light, I'm going to see just almost blue light. The light is spreading out here, and we see a little bit of red, we see a little bit of green, but it's mostly blue light because this is a blue LED, and these LEDs are particularly good. So I can really rip the light apart and see that blue light is made up just of blue light. And then, same thing with the green. Take a look at the green, and I see a little bit more, but it's mostly green. I see a little red on one side, I see a little blue on the other, but this is green. And then finally, I can take a look at red, and this is almost pure red light. Now, if we had a laser, we would see just a red dot in this. If I look at white light, I see a full spectrum. Now, we've got all the pieces here. We've got really the primary colors of light. We have what makes up light. We see that red, blue, and green, the way we look at it from our eyes is just red, blue, and green light. So how is it that the TV can see or produce all these other colors? So I've got this little handheld TV that we're going to take a look at, and I've got a couple magnifying glasses. Now, the TV has got pixels in it. And if I zoom in real closely, what I'm going to be able to see are these 3 colored pixels, the red, the blue, and the green. So I'm going to use a couple magnifying glasses. I could use one, but I'm going to use 2 because I'm going to be able to zoom in, and we're going to see that we've got, yes indeed, red, blue, and green pixels. Now, by turning these colors on and off, and also changing the relative intensity or the brightness of these, this is what allows us to produce all the other colors. Now right here, we see that I've got nothing on it because I turned the brightness up so that we can activate all of the red, blue, and green. So we're producing white light. So what we see here is the combination of red, blue, and green with the TV allows us to produce all the colors that you see. And also because of the red, blue, and green cones that we have in our eyes, we're able to see all the other colors in nature. So the TV is able to produce, because of red, blue, and green, all the other colors. Now, one little interesting experiment that you can do, if you have any colored filters at home, maybe if you've got colored saran wrap, you can do some interesting effects. So I'm going to make it really simple on this last demonstration. I'm just going to use a green light. And if I put a green filter in front of it, the green light goes through the green filter, nothing's absorbed, green continues going on. All right, so this is like a pigment. So, but it does do something differently if I use a red filter. It turns out that red absorbs green light. It doesn't reflect it back, it doesn't let it through, so it appears to be black. Now, because the intensity of light is so strong, it looks a little reddish. There's still a little bit of red getting through because there's red coming out of that light bulb, but it's mostly black. And in contrast, yellow, everybody thinks it'll change the light to be yellow light. No, indeedy, because remember, we've got green and red makes yellow light. So the yellow is only absorbing a little bit of the red, which there's none in the green light, and the green passes through and it continues to remain green. So, turns out today we learned about the difference between the primary colors of pigments and the primary colors of light. Pigments, cyan, magenta, and yellow. Light, red, blue, and green. And that's all I have to say about that. So join us next time as we explore new questions on Galileo's universe.